Hello, I'm Sanjeev Lalwani, Chief Strategy Officer at Lynntech. We are based in College Station, Texas. Today, I'll be discussing our work on a structural battery concept under Topic N2 32-086 in support of Syscom NavAir. As unmanned aerial systems continue to evolve, the demand for longer endurance, greater payload capacity, and improved efficiency is increasing. At the same time, size and weight constraints remain critical design drivers. This presentation covers a multifunctional materials approach, integrating energy storage directly into load-bearing structures with the goal of improving performance without adding mass. Today, I'll walk through the operational need driving this effort, our technical approach, the current maturity of the technology, and potential transition pathways. Lynntech was founded in 1987 with a mission to nurture and harvest scientific creativity into life-changing technologies. We are about 110-person strong advanced technology development company with deep experience in power systems, ruggedized electronics, materials science, and integrated systems engineering. We maintain over 66,000 square feet of facilities, including approximately 45,000 square feet of laboratory space. Our team includes more than 30 engineers, roughly 25 PhDs, and dedicated commercialization and manufacturing professionals. Importantly, we have a proven track record of moving technology from early-stage R&D through commercialization and government transition. We were honored with the 2016 Tibbets Award for Outstanding Contribution to the SBIR program. For this effort, we are applying our expertise in advanced materials and battery systems to create a multifunctional structural solution tailored for unmanned aerial systems. The Navy's objective is to develop novel integrated multifunctional materials and lightweight structures to enhance the performance of small unmanned aerial systems. UAS platforms are playing an increasingly critical role in modern operations. As sensing, communications, and autonomy improve, expectations for endurance and payload continue to rise. However, every additional capability typically comes at the expense of weight. The challenge is clear: increase capability, maintain or reduce structural mass, improve range and endurance, and do so using materials that are manufacturable and scalable. The initial transition target identified is the VXE-30 Stalker platform, though the broader opportunity extends across fixed-wing UAS systems. Our structural battery concept is designed to directly address these constraints. At its core, this effort aims to advance UAS performance by integrating energy storage into the aircraft's load-bearing structure. Traditionally, batteries are housed in the fuselage, functioning solely as energy storage. Our approach relocates energy storage into the wing structure itself. By moving the battery mass into the wing, the weight is directly counteracted by lift, bending stress on the wing can be reduced, and structural efficiency improves. This shift provides cascading benefits. For example, reducing mass in the fuselage can lower total aircraft weight or create space for additional payload. Lower weight, in turn, reduces required lift, which can extend flight time. Additionally, stress reduction at the wing root may allow structural optimization, further improving system efficiency. The structural battery is intended for fixed-wing UAS, where these aerodynamic and structural synergies can be fully realized. Lynntech's structural battery is based on a pouch cell architecture, enhanced with improved structural properties so it can function within a load-bearing member. A key innovation is Lynntech's interfacial layer, which bonds the internal anode, cathode, and separator layers to increase shear strength within the cell. This approach enhances structural performance while maintaining electrical functionality. Unlike traditional structural battery concepts that sacrifice electrochemical performance, our goal is to preserve battery capability while enabling mechanical integration. The structural battery modules are incorporated into hollowed wing sections, replacing non-load-bearing structural volume. This design moves load closer to the source of lift, reduces wing stress, and creates potential gains in payload and range. Importantly, the interfacial layer can be manufactured using processes similar to existing commercial separator production, supporting scalability and cost control. We are currently focused on development tasks to demonstrate feasibility. Initial shear testing of cells incorporating the interfacial layer shows promising mechanical strength improvements. Electrical performance remains close to commercial off-the-shelf pouch cells, indicating that structural gains are not coming at the expense of energy storage capability. Multilayer cell development is underway. The current technology readiness level is TRL2. However, projected progression includes TRL3 by October 2025, TRL4 by June 2026, and TRL5 by April of 2027. At this stage, no formal program of record has been identified. However, the effort is endorsed by NavAir, and future funding may involve partnership with a UAS manufacturer. Our focus is systematic risk reduction and demonstrable performance validation. This slide highlights projected benefits using the RQ-11 Raven as a representative example. Even modest structural weight reductions in UAS platforms can generate meaningful improvements in performance. Preliminary modeling indicates reduced overall system weight, increased payload capacity, improved range, and significantly reduced wing stress. The reduction in wing stress is particularly important. If the wing does not need to carry as much bending load, overall structural requirements may decrease. That creates opportunities for further weight reduction and efficiency gains. From a manufacturing standpoint, the ability to integrate the structural battery using similar processes to commercial pouch cell production supports cost control. Additionally, only the center section of the wing would require modification in certain platforms, minimizing disruption to existing manufacturing lines. Together, these factors provide both technical and practical advantages. To move beyond feasibility, follow-on funding will be required. A Phase 2.5 SBIR effort would enable integration of the structural battery into a UAS system and demonstration in operationally relevant conditions. Key steps include partnering with a UAS manufacturer, demonstrating in-flight performance, validating structural durability, and confirming electrical reliability under operational loads. At present, we are actively seeking a primary transition advocate to help move the technology forward. Identifying the right platform partner will also be critical. Beyond Navy UAS applications, structural batteries have broad dual-use potential. Any structure that requires onboard power presents an opportunity for multifunctional integration. Potential markets include other unmanned aerial systems, electric vehicles, robotics, and space platforms. In electric vehicles, integrating batteries into structural elements such as floors or doors could increase range without increasing mass. In robotics, reduced weight improves efficiency and agility. In space platforms, any reduction in mass has an outsized value. This concept is not limited to a single platform. That is, it represents a materials architecture that can scale across industries. To transition this technology, multiple pathways are possible. The most direct path would involve partnership with a fixed-wing UAS manufacturer for integration and testing, potentially starting with the VXE-30 Stalker platform. Alternative UAS platforms with vertical takeoff capability could also serve as integration targets. Funding pathways will require continued NavAir engagement and may include cost-shared development with a manufacturing partner. Additional options include licensing the manufacturing process to an experienced battery production organization. Other long-term expansion paths could include ground vehicles or space platforms, depending on application requirements. Our goal is collaborative integration and not isolated development. To conclude, small unmanned aerial systems are increasingly constrained by weight and endurance trade-offs. Traditional battery placement limits structural efficiency. Lynntech's structural battery concept integrates energy storage directly into load-bearing components, creating the potential for reduced system weight, increased payload capacity, extended range, reduced wing stress, and scalable manufacturing. This approach represents a shift from adding capability to redesigning how capability is integrated. We believe this technology offers a practical and forward-looking path to improving UAS performance. Thank you for your time and consideration. We welcome collaboration and would be glad to discuss integration opportunities further.